Welcome to the third part of the morning session about unsupervised learning, dimension reduction and data integration. We've talked about PCA, principal component analysis, and we've seen PLS, partial least squares. In this session, or in this part, we will talk about two-way orthogonal PLS, O2PLS. In particular, we first are going to look at population models for PCA and PLS. And then we're going to talk about multi-omics data integration techniques based on O2PLS. So we've seen PCA and we've seen PLS. We've looked at them from an algorithmic point of view, meaning we have some data as input and we have a solution to a maximization problem, and this gives us some numbers that mean something. However, in statistics, we are often interested in the population. What's the underlying population model of PCA and PLS? For example, what are the random variables and what are the parameters? A population model for PCA can be written as follows. We have X, our dataset, and this is equal to T, the scores or the PCs, times W transpose, where W are the weights or the loadings, plus some residuals. So here this means that X is explained by the product of scores times loadings, meaning that variation in X is caused by variation in the scores through the weights or through the loadings. And these loadings are the parameters. So these loadings are the parameters of interest. E is a vector of residuals, and the parameters W are estimated such that the variance of X times W is maximized. So the way to estimate these parameters is maximize the variance of X times W. We have a similar model. Again, we have X is T scores times W loadings transpose plus E, and E are the residuals. We add also for Y, because PLS looks at X and Y, so we add for Y is U times C transpose plus F. So U are the Y scores and C are the Y loadings and F are the Y residuals. Now we add the third equation, namely U is T times a regression coefficient matrix B plus H, some residuals. Because without this third equation, we would simply have two PCA models, where X, this is a PCA model for X, and this is a PCA model for Y. So we need this extra relation between T and U, between U and T, to actually make sure that in the model there is a relation between X and Y. So the T and U are latent or hidden scores, also known as joint PCs, because they look at the joint relation between X and Y. W and C are weights or loadings, and these are the parameters. And the relation between X and Y is fully captured by T and U through this third relation. So T and U fully explain the relation between X and Y. The parameters are estimated such that the covariance between XW and YC is maximized. So the parameters W and C, we can estimate them by maximizing the covariance between XW and YC, as we've seen before. Now, how to interpret this model? Let's make it a bit more specific. So X and Y are two data sets, let's say genetic and metabolomic data. Now T and U are latent variables underlying these data. And these latent variables vary. So variation in these latent variables in T and U cause variation in the two data sets, X and Y. And this, or put it differently, variation in x and y is caused by variation in t and u. And this is through w and c. To give an example in the above context, so genetic and metabolomic data, T and U could be genetic and metabolic pathways of several connected genes and metabolites. So T, as we've seen before, is a combination of genes, let's say, and a pathway is a combination of genes. So a genetic pathway is actually a combination of genes. So T could represent a pathway. And the same holds for U, that could represent a metabolic pathway. And variation in T and U, so because this pathway changes, goes up or down, depending on the needs of the cell, the gene expression and the metabolite abundances change. And additionally, W and C tells us which genes and which metabolites are most involved. So if T and U change, which genes and which metabolites are actually most affected or most important for the relation between T and U. So PCA models the variance of X or the variance of Y separately. PLS models the covariance between X and Y. Now suppose that both sources are present, meaning part of the variation in X is actually related to Y, and another part of the variation in X is just specific to X. For example, in X we have some pathways that contain genes that are correlated to metabolites. So that's the part that's related to Y. And in X you have other pathways that are just there for self-maintenance. So they go up and down because to keep the cell alive, basically. So they have nothing to do with the relation with the metabolites, but they are still important for X. So part of the variation in X has to do with Y, and another part is just important for X and not for Y. Now, in omics data integration, we want to capture both parts at the same time. Right? So because PLS doesn't capture this omics-specific variation, and PCA doesn't capture the covariance. So we need to extend the PLS model to also accommodate omics-specific variation. So this is the O2PLS model. So if you look carefully, you recognize the PLS model. However, there are data-specific parts being introduced. So now X is, let's say, a joint part, represented by T times W transpose, plus a specific part, T specific times W specific transpose, plus residuals. And the same for Y. So Y is partly a joint part, plus a specific part for Y, plus some residuals. And again, we have the relation that links T and U. Now that's a linear relation between T and U. So in addition to the PLS joint weights and scores, these ones, the T and the U, we have also specific weights and scores. And still, the relation between X and Y is fully captured by T and U, because as we've said before, TS and US do not explain the relation between X and Y, but they are just there because they are important for X or Y specifically. Now the parameters here are again the loading, so W and C, but also the specific loadings, WS and CS. To estimate these parameters, this goes in 3 steps. The actual details are a bit too technical, but in general, you can say that we first estimate several PLS components, and they will contain both joint and specific parts. From that, we estimate specific parts only and subtract. And how exactly you do that, that's part of the technicalities that I didn't mention here. And finally, because now you know the specific parts, you subtract that from the data and you estimate with PLS again to obtain only the joint parts, because the specific parts are filtered out. Now, the actual estimation procedure, you don't have to do it by hand. There is software available. It's called Omics-PLS. With Omics-PLS, you can also fit PLS, but also, in this case, O2PLS. One important thing that we didn't mention is how to find the optimal number of components. So how many joint components do we need, and how many specific components do we need? Yeah, so for PCA, this would be just the number of PCs. For PLS, it's the number of joint PCs. And for O2PLS, we have three numbers. First, the number of joint PCs, the number of X-specific components, and the number of Y-specific components. Well, one way to do this is to do cross-validation. This is actually something that comes in the next session. Cross-validation, very roughly said, works as follows. You pick a number for the, let's say for the joint PCs. You evaluate the performance of PLS or PCA or O2PLS on an independent test set. And you do this a lot of times. And you do this for different numbers of components. And then you compare which number of components gives you the best performance. And that's then the optimal number of components. So to summarize, for given data sets X and Y, we want to inspect their relation. And this can be done with PLS. However, we also want to capture data-specific parts. And this is something that PLS cannot do. O2PLS estimates joint and specific parts. And these parts consist of weights and scores, similar to PLS and similar to PCA. And one can interpret or plot the weights and the scores to understand which features or samples are most important. So as mentioned before, you can look at the weights for each gene and see if there are outliers, so very important genes or genes that have weight 0. Or you can also look at whether you see groups of genes clustered together, groups of weights. Or you look at the scores to see outlying samples. For example, one sample was wrongly measured or something else. Or you can see whether there are groups of samples. In this case, you might have, for example, batch effects or some kind of population mixing in your data. This was the third and final part of the morning session. Thank you very much for your attention.